So if you remember last time we were talking about file systems and how file systems place data on disk, how data is organized. We looked at three structures, actually four. Contiguous allocation of files. We looked at a linked list organization for the file system where files are organized as linked lists. We looked at an index structure for files, and we looked at a multi-level index structure for files. Okay, so that part of the discussion related to how data is stored, okay, on disk. What we are going to do today is to look at what the file system needs to do in order to retrieve data efficiently. And both of these look at this problem of trying to reduce the seek and rotational latency over it. Okay, so this is the picture that I had shown maybe 2 classes ago. Yeah, so that's a typical splatter of a disk. It looks like a CD. Okay? Data is organized in concentric circles. And we said whenever you need to access any data, you first need to move the head to the right track, position it on the right track. The disk is spinning. So you need the right sector, which is the chunk of data you're trying to access, to spin by under the disk. At that point, you can read or write data. Okay? So for every I/O that you send to a disk, there is a seek overhead. There is a rotational latency overhead. Okay, that is wasted time where the disk is not doing anything useful. Okay, you're simply trying to get to the data. Once you're at the right location, you can actually transfer the data. Okay? So typically an I/O time that for a disk consists of a seek overhead, the rotational delay, and the transfer time. Okay, this is the only useful part of the I/O operation where you are actually doing useful work. Okay, and the other two operations are simply overhead that you pay in order to access your data. Okay, so what we will do today is again look at when there are a sequence of requests coming into the disk, how should the disk service them in order to reduce the seek or the rotational latency or both. Okay? The lower this part of the I/O overhead, the higher the throughput of your disk, the more the number of requests it will be able to service per unit time. Okay, so here are some disk parameters. They're somewhat old now, but they're represented. I mean, disks are now terabytes, maybe 3-4 years old when disks were maybe 200-300 gigabytes in size. But this is just to illustrate the typical hardware parameters of a disk. So when you have a hard disk on your PC, not a SSD, solid state disks, as I said, are very different. These are traditional magnetic hard drives. Okay? So you'll see that this data disk has 16 splatters. Okay, so that basically means think of it as like 16 of these splatters that are stacked one on top of another. Okay, and they're all spinning. Okay, they have 16. So this disk has 16,000 tracks. Okay, so that basically means there are 60. So if you look at this surface, there are 16,000 of these tracks. Each track will hold some bits. Okay, so 63 sectors per track. 512 bytes per sector. Okay, this is the speed at which the disk is spinning. That's how fast the motor spins. That's a 7200 RPM disk. Today disks go all the way up to 1500 RPM. Okay. The more faster you spin, the more energy your disk is going to take because the motor has to work faster to spin faster. Okay, so the faster you make the disk, the rotational latency will come down because the disk is spinning faster, but it's going to consume more power. So it's going to consume more energy. Yeah. Average seek time around 4 milliseconds. Rotational latency around 4 milliseconds. Average. Okay, so every I/O operation will incur on an average that overhead. So 8 milliseconds, nothing is happening in terms of actually reading or writing data for every disk request. Okay. Now go back and think about demand paging or any file request. So that's the tax you have to pay in order to retrieve something. And then something useful will happen when you read or write sectors. Okay, once you are positioned the disk head on the right sector, that's the speed at which you can actually read off the disk, of the surface. There are buffers on disk which will cache data for you. Okay, we'll see what you can do with those buffers, what optimizations you can do. Okay, this is a typical parameter for 3.5-inch disks. Today's laptops take even smaller 2.5-inch disks. And so on. Okay, so disks are getting somewhat smaller, but they are also increasing in storage capacity. Okay, the way you increase storage capacity is if you can actually make the electronics smaller, the disk head becomes even more smaller that it can read or write even at a more fine-grained basis. You can have more tracks. Yeah, because and then if you have more tracks, you can record more data on the disk. And as the electronics gets better, the capacity density of bits that you can record on this sectors as well as tracks increases, and you can store more data. Okay? You can also pack more platters. Okay? So if you can actually make this surface thinner and in the same thickness, you can pack more of these platters, you will have more storage capacity. Okay? The way disks become higher in capacities, either the disk head becomes more precise and thinner, so you can have more tracks, or you can basically, if you can reduce the thickness of these platters, okay, you can put more of them inside a hard disk. Okay, and then if instead of 16, if you could put 32 platters, you doubled your capacity. Okay, that requires you to make the technology better and put more of these into a disk. Okay, this is just an aside to keep in mind. Okay, so what we will really want to worry about is how do you account for this overhead, the seek and the rotational latency, whenever you want to retrieve. Okay, now the storage part is done. Okay, you have picked the file system layout, whether it's contiguous allocation, whether it's linked list organization or multi-level index. Any of the things that we studied last time is being chosen. The disk is storing data from your file system. And what we are going to do today is simply IO requests come into your disk. How should it service those requests in order to reduce those overheads? You can't move the data around. The data is where it is. What you can do is try to service it in a smart way to reduce those overheads, and that's what we are going to look at. Any questions on this parameters? Okay, so here are some ways by which you can reduce the seek and rotational latency overheads. Okay? Some of these are technology improvements. You can't do anything as far as the OS is concerned, and some of those are OS optimization. You can make the disk smaller. Okay? So for instance, instead of a 3.5 inch platter, you can make a 2.5 inch platter. Okay? And then that is going to simply reduce the seek time, because there is, if this think of it as a CD half this size. Okay? The CD is half of this size, then the amount of time it will take for the diskette to move from the outermost to innermost track will reduce, because it's a smaller platter. Okay? So now seek time, the average seek time is going to go down as a result, because you made the disk smaller. Okay? You can make the disk spin faster. If this platter is spinning faster, it is going to reduce the rotational latency. Okay? So here we saw a disk with 7200 RPM speed and a 1500 RPM. This is almost twice the speed. So it's spinning twice as fast. If it spins twice as fast, each rotation is going to take half the time. Okay? That is going to reduce the rotational latency. Okay? So you can use faster disks, smaller disks. Yeah, but assuming that you have chosen a disk, it's already installed on your machine, you can't change those facts. Those are hardware features. Then the only thing you can do are schedule operations to minimize disk over movement. That's what we are going to look at today. Okay. You can also lay out data so that related data is on nearby tracks. Okay. Think of files, blocks of a file. If you store them close to one another, they don't have to be contiguous, but the closer they are to one another, because these are related set of blocks, they're likely to be accessed together. Okay, if you read the whole file into an editor to edit it for, let's say, to change your code or whatever, you're going to retrieve all of those blocks. The more scattered the blocks are, the more the disk head has to move back and forth to retrieve data. Okay, and the closer it is, even though it may not be contiguous, the less disk movement you are going to see to access all of those blocks of the file more or less together. Okay. You can then also cluster files together. Okay, so if you have files in a directory, instead of scattering them, you can put them close to one another. Okay, if you're doing backups or whatever, you may want to basically keep them together so that the overhead in accessing them is going to be low. Now, those are not requirements, those are simply optimization. Because we said we are going to use blocks and we don't require the blocks to be contiguous, it is okay if you spread them out, but it only increases the overhead. Okay? The more you cluster data that's accessed together close to one another on disk, the lower the overhead is going to be. Okay? You can also choose the block size or sector size. I think we had a quick discussion on this last time. The larger the sector, the less your overhead is going to be. Okay? If you have a larger block size, okay, you have to pay one seek for each block. Okay? and that's independent of the block size. If you make the block size bigger, after one seek, you can access a larger chunk of data. Okay, so larger block size will amortize the seek overhead over some number of bytes that are retrieved from a file. Okay. Smaller block size allow you to do more interleaving, okay, reduces internal fragmentation in files and so on and so forth. Okay, so there are those overheads as well. Okay. Now all of these are true for traditional magnetic hard drives. If you have a solid state disk, okay, some of these considerations go away. You don't need to make the disk smaller. It's not spinning. It's simply you can access the data on disks like you access RAM just through an address. Yes, question.
When you do seek, is the CPU free that time?
Okay. Question is, when you do a seek, is the CPU free? Okay, so we'll look at I/O devices maybe at the end of today's class, how they work. So typically what happens is, for any I/O device, there's a small I/O controller. Think of it as a tiny CPU that's embedded on the device. It's called I/O controller. For a disk, you'll have a disk controller. Okay, the way I/O operations work is the CPU will simply issue a request to the I/O controller saying, go read or write this block. Okay? And then it will go off and do something. Okay? And it's the I/O controller's job to execute that command. Okay, you say, go read sector 10 on track 50. That's a request you may issue to a disk controller. Then the disk controller will actually move the disk head to the right location, read it, and once the data has been read, it will interrupt the CPU saying, here the data is read. Okay? So CPU is typically not doing a whole lot other than issuing commands. Okay? Other than the most trivial devices which don't have a controller at all, in that case the CPU has to do all the work. Any sophisticated I/O device has its own I/O controller, which will be responsible for executing I/O commands. Okay. All right. So now we are back to disks. Okay, so how do you reduce access time? So we'll look at maybe these two considerations. The other are hardware choices you make. Okay, there's not much you can do. Okay, so we'll look at this problem of disk head scheduling, which is essentially the following problem. Assume that there are several applications on your machine. Okay? Each application may have one or more files open for reading or writing, and they're concurrently reading or writing to their files. Okay? So from a disk's perspective, there are all these requests coming from any application that has open file that's accessing this data. Okay? So at any point in time, you may have some number of I/O requests that have come from different applications on your machine. Okay? And the question is, and that data that you are accessing may be scattered all over this disk. Okay, for now, let's assume it's only one platter, simple disk. Okay? And the question is, in what order are you going to service these I/O requests that have come in? And we'll see that the order actually matters from an efficiency or a performance perspective. Okay? So we'll look at this problem is referred to as disk head scheduling. You're simply scheduling or deciding in what order some requests that have come in are going to be scheduled by the disk. At each point in time, you can service one request. You can say, go to this location and read that data. And you say, go to another location on disk, read that data. Okay, so we want to decide that order. Okay. We'll look at 4 different techniques, okay, scheduling algorithms, and then a couple of other variants of those techniques. So we'll have 6 in all. Okay, so we'll start with some very simple ones and then start looking at more sophisticated techniques. So first one, very straightforward. This is always our first technique. First come, first serve. Okay? First come, first serve technique does not actually reorder requests. It's simply servicing I/O requests in the order in which they arrive at the disk. Okay, the disk controller is receiving requests. It's simply servicing them in that order. Okay. Now, I should also mention that the algorithms that we are going to look at here are only optimizing seek time. Okay. They are trying to minimize disk head movement in terms of seek. They are not optimizing the rotational latency. I'll talk about a few techniques that will also reduce the rotational latency over. Okay. There are 2 of these overheads we need to deal with, the seek and the rotational latency. These are simply looking at seek at the moment. They are not looking at rotational latency. I will tell you a little bit about how you can address both together. Okay. So let's start with the simplest one, which is first come, first serve. So this is basically a layout. Okay. So think of it as this is your disk. Okay, so I'm simply basically looking at a set sort of a scan from the innermost. So this is the innermost track, that's the outermost track. This is a circular disc. I'm simply showing a small layout of that disc, okay, just for simplicity. And these are the track numbers. Okay, they go from 0 through 100 here. Okay, the innermost track, which is basically this track here, is track 0. The outermost track, which is that track, is track 100. And we have requests coming in. Okay, so the requests are, there's a request for some data on track 65, 40, 18, and 78. Okay, so and then we are using FCFS to service these requests. Okay, and we want to compute how much has the disk head moved back and forth, how much work did the disk head do to service this request. Okay, so first you need to know where is the disk head currently. So when the first request comes in, we say that disk head is at track 30. That's where it is. Okay, now request for 65 came in. So what you will do is you'll say go to track 65, seek to track 65. So the disk head is actually going to move outwards and go to track 65. Okay, that's 35 seeks in terms of, so if it's here, you're going to simply move out, okay, to track 65. Okay, so you go to track 65, you read that data. Next request is 40, so you're going to move back all the way to 40. Okay, and then you have 18, so you're going to then move all the way to 18, and then 78, so you go move back all the way to 17. Okay, so you're basically going to move back and forth to service those requests. Okay, so the order in which you service them is the same as the order in which they came in, 65, 40, 18, 78. And if you look at how many seeks, how much distance did you move? So from 30 you went to 65, that's 35 tracks. Okay, and you went to 40, that's 25 tracks. And you went to 18, that's 22, and then you went from 18 to 78, that's another 60 tracks. Okay, so you moved. Okay, the amount of work you've done is 142 in terms of the tracks you traverse to service these requests. Okay, very straightforward technique. It's not doing anything smart. It's simply servicing requests in the order in which they're coming. Okay, is that clear? I will mention that this is not a good algorithm for magnetic disks, okay, because it hasn't done anything in terms of reducing the amount of distance the disk head has moved, but it's a fine algorithm for SSDs. Okay, what you actually have in more modern machines are solid state disks. There are no moving parts. So there's no overhead for jumping from one track to another. Okay, data is simply laid out like it's stored in memory. Okay, you can simply go to any random location and read what is stored there. There is no overhead. Okay, so there is no need to reorder requests if there is no overhead. So for SSDs, the simplest works just as well. There's no need to do anything smart. For traditional magnetic disks, you have to do something more than this if you want to optimize performance. Any questions on this? Okay. Next up, shortest seek time first. Okay, SSTF. Yeah, this is what is referred to as a greedy algorithm. If you've taken 311, you should know what greedy algorithms are. At least you should have heard this term. Okay, what it simply does is it looks at where the disk head is currently. It looks at all the requests that have come in, and it says what is the nearest request to the disk head. Okay, and go there and service that request. Okay, so you always go to the closest request, closest outstanding request, and read that data. Is that clear? Okay, so then, if that's, then let's assume the same request came in, which is, you write that down. 65, 40, 18, 78. Okay, those are the requests that have come in at some point in time. The disk head is at location 30, and you are using SSTF. So which is the first one you are going to service? 40. Okay, so you have to see the disk head is at 30. You look at, evaluate which is the closest request. This request is 10 tracks away. Okay, you're at 30, that's at track 40. Okay, this one, 30 minus 18. Oh, arithmetic. This is 48 tracks away and this is 35 tracks away. So 40 is the closest one. So you go to 40. Okay, service that request. So that's done. You still have 3 requests outstanding, which is 18, 78, and 65. Okay, you are at track 40. So you'll see that track 18 is the nearest track among the outstanding requests. So you are going to go from here to here. Okay, service that request, and then there are two more remaining. If you're at track 18, then it should be clear that 65 is closer to you than 78. 78 is further out. Okay, you are here, 65 is here, 78 is here. So you go to 65, service that, and then you go to 78. Okay, so this is the order in which you service the request: 40, 18, 65, 78. And now you look at how many tracks did your diskette traverse. Okay, you went from 30 to 40, that's 10. Then you went to 18, that's 22. And 18, you went to 65, 47, and 13. So you traversed 92 tracks overall. Okay, so you see that now you've done less work than first come, first serve, 142 tracks. Okay, that's more distance you have to move back and forth. Here you moved only 92. Okay, fewer seeks, that is lower seek overhead. Okay, so you will basically, these requests will complete faster if you use SSTF than if you did FCFS, simply by the virtue of the fact that the disk head has to move less distance to service them. Is that clear? Okay. So this is a greedy algorithm. Okay. It has a certain, so it is going to do better than FCFS, but it does have the potential for starvation. Okay, and here is why. Okay, so you can assume, so let me just draw a small disk here. Okay, the disk head is here. Okay, and then there are all sorts of random requests. Okay, since you're always going to pick the closest request, it may be that there are always requests that are close to the diskette, so the diskette is simply moving back and forth at some region, and there are requests that are come in that are far away, either on the outermost or the innermost track, that are always further away than some other requests, and they will never get serviced as a result. Okay? If there is always a nearby request, some request that is far away will be less favored because you are always going to the nearest request. Okay, just as in shortest job first, if you always have a shorter job, long job star. In shortest seek time first, if you have a nearer request, the requests that are further away will have the potential to starve. Okay, so starvation is a problem that you have to deal with in shortest seek time first. If you have a heavy load and there are constant stream of requests coming in, and some of those requests happen to be close to the disk head, some other requests that are further away will starve. Is that clear? So, as I mentioned, this algorithm only tries to optimize the seek time. Okay? There's a variant of this algorithm that is going to that's going to optimize rather both the seek and the rotational latency. Okay, so the problem that now you have to solve if you want to do something more sophisticated is as follows. Figure out question.
Even for just seek time, it's not optimal, is it? Even if you ignore rotational time?
Even for seek time, is it optimal? It may not be optimal. Okay, I didn't say it was optimal. I just said it will try to reduce seek time. It's greedy, but it's not necessarily optimal. A question there? So now let's say you want to take shortest seek time first and generalize it to optimize both the seek time and the rotational latency. Okay, so we'll assume that the diskette is currently here. Okay, and then you look at where are the requests that are coming. Let's say there's a request here. Use a different color. There's a request here, there's a request here, there's a request here, there's a request there. Okay, those are the sectors that you need to read, and the disk head is currently positioned here. Okay. If you want to simultaneously optimize both the seek time and the rotational latency, okay, what would you do? Okay, building on this simple idea, but you only look in here. We only looked at seek time. Yes.
We need to first figure out what the rotational delay is.
Okay, so you need to determine what the rotational latency is.
I guess starting with that, you use something like this without counting in the rotation delay, and then as you're doing seeks, you calculate the time it takes for rotation, and then once you get enough of that, you can back that as well.
Okay, So the point being made is you want to factor in both the time it takes to seek to a track as well as the time it takes for the rotational latency once you get there, and try to optimize the sum of the two. Any other points, thoughts on this? Yes.
While the disk head is moving back and forth, the disk is still spinning, so just the sum wouldn't be good enough because you get some rotational work done while the disk head is moving.
Yes, so that's a good point. So keep in mind that this is not a static fixed surface, right? It's not like it's going to stay like this. The disk is constantly spinning 15,000 rotations per minute. Okay? So what you really need to do is to understand where the disk head is, not just the track, but the exact sector. And say, if you were to move, let's say, to this track, okay? You'll get there in a certain point, get there at a certain point in time. When you get there, what is the sector that's under the head, and how long will it take for this sector to spin back? Because when you move here, this sector would have actually rotated, it may be here at this point. So you may have to wait for an entire rotation for it to come by. It looks close by here, but since the disk is spinning, you have to keep that in mind. That what is the situation as it appears now may not be the case when the disk head has actually moved a particular track, because the disk is constantly spinning. Okay? But assuming you can keep track of where you are currently and where would this each of these sectors be if you actually went and to those tracks, you can compute the seek time to go to, let's say, track I, as well as the rotational latency for that sector to spin by. If you knew exactly where you were and you knew exactly how much time it would take you to get to that track, you should be able to compute, given the speed of the disk, how much time it is going to take for the sector to spin by. Okay? And then you can estimate the rotational latency. Okay? So if you did this computation, then what you could do is not just do shortest seek time first, but do something like shortest access time first, or the nearest request first. Okay? So there's a variant of this called SATF, which simply looks at the seek plus the rotational latency for each of those requests and say what is the closest request in terms of the sum of the seek and the rotational latencies. Okay? Keeping in mind that the disk is spinning, so you have to account for when you get to a track, what is the rotational latency you are going to incur. So you basically don't just look at the distance in terms of seek, you look at the distance or the time it takes in terms of both the seek and the rotational latency. Okay? So you compute, given the disk head at this point, what is the access time to get to this sector, that sector, that sector, that sector, and then pick the nearest one and then go and read that data. And you repeat. Okay, is that clear? So that is the order in which you are going to service those requests. Okay. Now, if you think about this problem actually maps onto a nice problem in theory, which is referred to as the traveling salesman problem. I assume you did this in 311. Okay. If you thought about TSP, traveling salesman problem is simply the problem of if you are at a current location and you want to visit a few different locations, in what order are you going to visit them so that the total distance is minimized. That's exactly what we are trying to do here. Okay, we are trying to minimize the total access time. So you want to basically find a path to traverse all of these locations such that the total distance that the disk head is going to traverse, or the total time in this case that you spend to get there, is minimized. Okay. So shortest access first is an instantiation of the traveling salesman problem in disks and operating systems. Now you will not actually solve the entire TSP in hardware because that's going to be computationally expensive. You will use some approximations to do that. Yeah, because making this computation is, as you can imagine, not a trivial task. You have to actually keep track of where is the disk head, where is it going to be when you move to a certain track. And so. But be that as it may, it is still an instance of a TSP. Okay. All right, so that's shortest seek time first. Okay, so that's our second technique. Here is the third one. It's called scan. Okay. This is best understood by thinking, this is also referred to as elevator scheduling, incidentally, and is best understood by what happens when you have an elevator, okay, that is servicing this elevator in a building. Okay. That's simply servicing requests for people who are trying to get in, let's say. So your elevator may be moving up or moving down. At some point it's at a certain location, and there are random people on random floors that have requested the elevator. And then you have to think about how does the elevator service these requests. If you think about how elevators work, they're simply going from the top to the bottom and the bottom to the top. And as they pass any floor where there's an outstanding request, they're going to stop. The elevator stops. Okay, people get in or get out, and it continues. Okay, so it may go from the top floor. As it's going downwards, it's going to stop at each floor where there is a request to get in or get out. And then people get in, and then it continues down. It goes all the way to the bottom floor. Okay, and it reverses direction and it goes up. So it's simply scanning all the floors going back and forth. Okay. Scan scheduling is actually the same algorithm used in disks. Okay, your disk head is simply going to scan, basically keep scanning back and forth. It's going to start at the innermost track, keep traversing outwards. As it reaches any track where there's an outstanding request, it's going to pause, okay, service that request and continue. Let's continue all the way to the outermost track, okay, and you reverse direction and start scanning inwards. Okay, so you simply scan back and forth. So you'll just go sweep, okay, sweep all the way to the back. Each time there's a request to pause, continue sweep. And you change direction, you sweep back and forth. So you just keep doing this and just service your request. Okay, is that clear? So you are not ordering requests per se, you are basically letting requests come in as they do, and you're simply scanning back and forth, and as you pass by a request, you service it. That's all you're going to do. Okay. Now here we are assuming that we are on track 30, same request. Okay, and you say the disk head is moving towards lower numbers, we are scanning inwards. Okay, so if you are scanning inwards from track 30, there's only one request here, which is 18. So you're going to go to 18. Okay, service that request. Okay, and technically what you would do is you will actually go all the way to 0, change directions, and then go service 40, 65 and 78 as you go outwards. Okay, so you go from 40 all the way to 0, and then you go all the way to 72. So you should, that's the way, 78. That's the number of tracks you're going to service. Okay. Now there is a variant of this elevator scheduling. Okay. This is called scan. There's a variant called look scheduling. And that variant, all that it does is it basically, if you service the last request, there are no more outstanding requests further in that direction. You don't go all the way to 0. You can change directions and just start sweeping backwards. Okay, think of an elevator that's going down. Okay, let's say it reached the 5th floor. As it was going down, it serviced the last request. There is nothing else to do. Then why go all the way to the bottom floor, then change direction, then start scanning up? There are requests from upper floors. You can change directions there and start going up. Okay, because you're not doing anything by going from, in this case, you are at 18. You serviced 18. If you are to go all the way to 0 just to change directions, you're going to waste 36 seeks just to change directions. Why not just from 18 say there's no more requests in this direction, but there are requests in the other direction. So let's just change directions at that point and see. This variant is referred to as look. In look, you don't go all the way to the innermost or outermost track. You go to the innermost or outermost request and then just change directions. Yes, small optimization. So the distance of seek here is assuming look. So which is why you only go from 30 to 18 and then you change directions and go the other way. If it was pure scan, you would assume that you went all the way to 0. Okay, so this would be more than 12 here. Yes, question.
Wouldn't that still be 12 and the 22
Yeah, right. So if you can go all the way to 18. So in some sense, what you've simply done is gone from 30 to 0, and from 0 you've gone all the way to 78. So you'll have 30 plus 78. So you're simply going this, and then once you reach 78, you're done. That's the number of seats. Okay, how you add that up is, whether you put this here or here is not important. You still travel those many tracks. Okay. So now the only thing that you need here is a sorted list of requests. As requests have come in a certain order, you have to maintain them in a sorted order so you know what's the next request you have to pass. So long as you do that, there isn't much else you need to do to implement this scheduling. Okay. And this is what most disks actually use. Yeah, this scan scheduling is what is implemented by the disk controller on hardware. Okay, the simplest optimization that the disks will perform. Shortest access time first, typically much more expensive to implement. Yeah, so the controller becomes expensive, disks become more expensive. People don't ask when you buy a disk if it's, you only look at how much, what's the storage capacity. You never say what is the disk scheduling it's using. Should I actually pay $10 more to buy something that's more sophisticated? So to keep disks cheap, the hardware is kept simple and it uses simpler algorithms like this. Okay. You could, of course, implement disk scheduling in software in the device driver and not do this in hardware. That incurs a little higher overhead in terms of doing this in software. Okay, there are some disks that simply have very basic controllers that don't do any scheduling. Okay, they simply implement FCFS. It's left to the device driver to do this reordering. Okay, in that case, you can implement more sophisticated schedulers. But if you're doing this on hardware, typically this is as good as you get in terms of sophistication. Is that clear? Okay. So here is yet another variant of scan called C-scan. Okay. All that this C-scan does is, again, you're scanning back and forth, okay, but you service requests only in one direction. Okay, so think of an elevator that only stops at floors as it's going down. Okay, when it's going back up, it simply just goes all the way to the top, doesn't stop at any intermediate floors. Okay, and then it's only servicing requests as you want to go down. Okay. The same is true here. You are going to scan back and forth, but you stop on tracks only when you're scanning outwards, let's say. Okay, once you reach the outermost track, you just do a big sweep all the way back. Okay, but then you don't stop even if there are outstanding requests, you just come back all the way to zero and then you start scanning outwards and then you start servicing requests. So if you service requests when you're only scanning in one direction, you have what is referred to as C-scan. Okay, is that clear? Now you may ask, why do this strange variant? What's the problem in servicing requests? If you are moving by a track and there is an outstanding request, why not service it? Why do you want to wait all the way to go back and do it only in one direction? It doesn't make sense for elevators, for sure. Right? If the elevator was only servicing requests when it went down and you actually want to go to a higher floor, you'll have to traverse down and then go back up and then wait for your floor to arrive on the reverse sweep. And that doesn't make any sense. But does it make sense for disks? Yes.
I think you can assume that the requests are going to be uniformly distributed. So both times.
Okay. So as was pointed out, the only advantage of using circular scan is it results in more uniform wait times for a request. Typically what happens is, if the requests are uniformly distributed, a request comes in, you can basically assume, if it's uniformly distributed, that it's with equal probability it can be any of those tracks from 0 to 99. Okay. Now in scan, what happens is requests that are in the middle implicitly get favored more, because on an average you will assume that the disk head is somewhere in the middle. Okay, so if your request is somewhere on the middle tracks, there's less disk head movement. Okay, if you're on the outermost track or the innermost track, you have to wait longer for the elevator to come to you. If you're somewhere in the middle, because the time you wait is actually lower because you will get serviced in either direction. And because of this fact, if you use circular scan, you are going to have more fair wait time. Everybody is made to wait uniformly at the same time. You are not going to favor the middle tracks over the outermost and innermost track. Okay, that's the simple reason why C-scan is actually used. If you want somewhat more fairness, you can use this technique. So again, what you will do here is, if you are 30, you are moving in, rather moving out. So you only service when you are moving out. You go from 30 to 40, 65, 78. Then you do a long seek back. Okay. You would technically have to go to 0, change directions, and then come to the 18. But if you have the look variant, you just come to 18 and reverse direction. Okay. Just as you have C-scan, scan has look, C-scan has the C-look variant. It doesn't go all the way to the innermost or outermost track to reverse direction, you go to the innermost or outermost request and change directions. And this distance is assuming that optimization built in. That optimization was not in there, you would go all the way from 30 to 100. That's 70 seeks. Then you just do a big sweep backwards, go all the way to 0. You sweep 100 requests, 100 tracks rather, change direction and then go to 80. And that would be the distance you would sweep. Here you only went from 30 to 78 and you changed direction and then went to 60 tracks. That's that. Any questions on this? Yes. Please.
How, like in practice, how does the distance of a seek affect the time it takes? Like, is it a linear relationship or is it more like a?
Okay, that's a good question. The question is, how does the time of a seek affect the time? Sorry, not the time. Sorry. How does the distance of the seek affect the time it takes? Okay. Now, this requires you to sort of understand a little bit of disk electronics. Okay. It is not a linear relationship. Okay. The way typically the disk head is going to move is somewhat similar to how a car moves from a sort of a stationary, let's say the car is stationary and you want to make it move, you're going to press the accelerator, the car is going to accelerate, okay? Then maybe you reach a steady speed and then you're going to coast and then you're going to decelerate. Okay? Same thing is true for a disk. I mean, this is basically mechanical parts. So if you want to do a long seek, you're going to basically make the disk head accelerate, okay? So it will spin up, not spin up, not spin is the wrong term here, it will speed up. Right? It will reach a speed, that's its max speed, and it will start coasting along. And then when it's about to hit the track, you start decelerating and then you basically stop at that track. Right? So it's actually a complicated relationship. It's actually a quadratic relationship. It's not linear. Okay, the time it takes you to traverse 20 tracks may not be the same as the time it takes you to traverse 10 tracks or 60 tracks. Okay, it is actually a quadratic relationship that is used to model this. Now that also says that short seeks are somewhat different, okay? Because you're just, let's say you want to just go to the next track. You're not going to accelerate and decelerate. You're just going to make a gentle move. This is like if you want to move your car 10 feet into a parking spot, you don't slam on the gas and then you accelerate and then you slam on the brakes. That's not how you drive your car. You slowly coast into a sort of move into the parking space, right? So that's the same way you will move your disk head. You will have a gentle move into the next track. Right? So depending on the distance, okay, it's not at all a linear relationship. But the general point is the more tracks you have to traverse, the more time it will take you. Okay, that part is true, but the time it takes you is not linear in the number of tracks. Yes.
So does it do that like gentle coast in order to preserve the disk life? Because it would be faster if it like slammed on the gas and then the brakes.
Yes. So I think that partly it is disk life, partly it's precision.
Okay.
These are mechanical parts, right? If you want to move it 1 millimeter, remember the disk is barely 2 inches and there are 16,000 tracks. So one track may not even be a millimeter away from the next track. It's much less distant. So if you want to move, let's say 1/10 or 100th of a millimeter, there is no way you are going to accelerate and decelerate. The electronics don't work that way. Right? So you're moving very tiny distances. So you have to just move it, just nudge it just so much to move it. Right? So that's basically how it works. Okay, is that clear? Any other questions here? Okay, so that's disk head scheduling. Okay, so what we have seen is basically our file system requests come in. What can you do to improve performance? And the basic point is try to reduce disk seek as much as possible. For your shortest access time first, like techniques, okay, TSP, you try to reduce both the rotational latency and the seek time. Okay, that's one set of optimizations you can do. There are a few others. Okay, one is referred to as disk interleaving. Okay, so disk interleaving is basically the problem of how do you store blocks that are accessed together close to one another on disk. Okay. Now it may seem like the best thing to do is to store, let's say, consecutive blocks. Let's say a file with 3 blocks. You may think that this is, let's say, that's a track. Okay, that's block 1, 2, 3. So you may think that if you want to store the file on this disk, the best thing to do from a performance standpoint is to store the blocks together. So you store the first block here, the second block next to it, and the third block next to it. Okay? And this may be good if you're trying to optimize sequential access, for instance. Now it turns out, although this seems conceptually a good optimization to pick, it is not a good optimization, even for sequential access. And the reason is as follows. Let's say you want to read all three blocks of the file. You open this file in an editor. Let's say it's Java code. This source code file has 3 blocks. You open it on an editor, so you are going to basically read the entire file, which is you'll send all 3 requests to the disk saying read all 3 blocks. Okay? So what the IO controller will do is instruct the head saying go to that track and read that block. Okay? So the disk head is simply going to move here and read that block. Okay? And the block is bits are being read in. Okay, once this request is finished, the IO controller will tell, or the disk controller will tell the disk and go read the next block. Okay? The next block is right next to this first block. Okay? But because the disk is spinning continuously and the next block begins immediately where the previous block ends, and there is going to be some finite latency for the IO controller to tell the disk read the next block. By the time the request comes in, the first few bits or bytes of this block may have spun by. So even though the block is right there, because of the latency to issue the next request, this block is already spinning by the disk. Okay, so in that case, you have to wait for an entire rotation for that block to come by again. Is the problem clear? So there are basically, so if you actually store them next to one another, you may not get the performance you seek because there is finite latency between receiving the bits of the first block and issuing the next request. And in that time, the disk head is spinning at 15,000 RPM. So some bits may have gone by. So you are going to have to wait. So there are 2 answers to this solutions to this problem. Okay? First solution is what is referred to as disk interleaving, which says don't put sequential blocks of a file next to one another. Leave some space. So if block 1 is here, leave that block for some other file and put the next block, maybe 2 blocks down. Okay? And then put some other data here and put the next block and another 2 blocks down. If you do this, then you read this block, and by the time the next request comes, you are somewhere in the middle. This disk is spinning, so you are somewhere here. So the next block is not yet spun by. It's going to spin by very quickly. Okay, so you can smoothly read this block, this block, this block, and so on. Okay? So this is referred to as disk interleaving, where you don't store contiguous blocks of a file or sequential blocks of a file contiguously. You leave some gaps. This allows you to account for the finite overheads that you are going to have to incur in servicing requests, and not have to waste time waiting for the block to spin by again. Okay? That's the first solution. Okay, what might be another solution? Yes.
You have different platters.
You do have platters. In this case, we are only looking at one platter. Same is true on any platter. It doesn't matter. What else could you do that may be an optimization? Basically, you want to reduce the overheads that you are paying in terms of either seek or rotational latency. In this case, it's rotational latency. Okay, so next optimization is very simple. You are just going to be greedy and read more data than has been requested. And this is referred to as read ahead. If you are paying 4 milliseconds of tax just to put the disk head there, okay, why just read one sector? Okay, you have a cache. Okay, remember I showed you at the very beginning and I said I'll come back to why there is a cache on your disk. Okay, you have some buffer on your disk. It's 8 megabytes or 4 megabytes in size. Let's use this buffer to do something useful. The useful thing we are going to do is essentially read ahead, which says once you read a track, once you reach a track and some sectors are spinning by, read some more sectors that are anyway spinning by the disk, under the disk. It doesn't cost you anything to read that because you're already positioned there. The disk is spinning. You're simply activating the disk head and simply reading bits, and they come and sit in the buffer. Okay? So you will actually, what you will do is, even though this sector that you want has already been read, the track is still, the disk head is still on the track, you continue reading all of the sectors that are spinning by, read them and keep them in a cache. Wait for the next request to come in. Okay? The next request says, okay, read the next sector that was next, adjacent to that sector, you already read it, there's nothing to do, it's in the cache. And then you read the next sector, that's also been read. So you simply just read more data than you've been requested because it's too expensive to wait for another rotational latency, or too slow rather, not expensive, or it takes a huge amount of time to move the disk head to that track. You have some buffer, make use of it, read more data. If you don't need it, you can throw it away. It's simply a cache. You haven't done any harm by reading more data than you need to. Okay. So you basically do what's called read ahead. In read ahead, you will basically read more data into the cache and then wait for the next request. So this is simply betting on the fact that if the file system did its job well and it stored related blocks close to one another, they may be on the same track. A request for the next block may come in soon, and the disk has already done the hard work. Okay, you're prefetching. Read ahead is a form of prefetching. So that's basically what you're done. Okay, you prefetch data into your disk buffer. So the next request comes, no more seek, no additional latency, data has already been read, hard work has been done, performance gets better. Okay, of course, if the next block was not stored here, it was stored on some other track, all of that data you read has to be thrown out, but they're no harm done because you didn't actually spend any seeks to read it. Okay, so this is disk level read ahead. I should also mention that the file system itself can also do read ahead at the file system level. So if the file system typically looks at access to a file and it detects that you are reading sequentially, okay, it will aggressively start prefetching for you. Even before your application has said, go read the next line of your file. Okay, remember that in this lab that we are just doing, we are simply opening each file and reading the entire file. These are words in the file from the beginning to the end. Okay, you are reading one word at a time. Okay. Your file system is intelligent enough to see that your readings, your requests are sequential. Okay. And if it detects sequential pattern, it assumes that you are going to continue sequential access and it will start prefetching for it. It will guess that your next request is going to be the next line in the file or whatever it is, or the next block. So it will prefetch, it will issue those commands even before your application issues those commands. It will prefetch. So you will do prefetching at the disk level. From the disk level, you prefetch in the OS level, and your data is already going to be in the buffer even before you actually made a request for it. Okay, this is simply going to optimize the performance of your application and optimize the disk seek over it. Okay. So you will have this read aheads or prefetching happening at multiple levels. This is disk level prefetching. It is simply to avoid this problem where if you store blocks next to one another, okay, you may actually have to wait longer if you issue requests one at a time. Okay. File system will also do prefetching once it sees sequential accesses at the file system level. So if you do all of these optimizations, you're going to get some performance. And all of this is because the disk is slow. Okay. You want to guess, you want to do some optimizations to help the performance of applications that are doing I/O. And disk seek, read ahead is one such optimization. Questions on this? So we looked at two of these optimizations. One is interleaving, okay, where you don't do read ahead. You simply keep some gap between consecutive blocks of the file if they are on the same track. This will allow you to reduce this problem of the disk sector has just gone by, so I have to wait for entire rotation for it to come by again. That gap allows you to smoothly read successive blocks one after another. The other thing you do, which does not require interleaving, is you can simply put in a read ahead optimization on your controller. Yes?
Do you ever use both of these together? Or like...
Both of these, you could use them together because, if you're going to read this and this, there's no harm in reading this. The disk head is already going to be seeing that sector spin by. Okay, interleaving is done at the file system level. So you allocate a block here, the next block is allocated there. Okay, that's simply taking into account that this is how disk works, so let's not do extra work by trying to be too smart. Okay. Read ahead is a disk level optimizer. It's saying I already paid the price of getting here, so I'm going to do a little more work and read data. So you can have them together. But if you have one, you typically don't need the other, but they are actually happening at two different levels. Okay, so last point we'll look at here is solid state disks. So as I mentioned, I brought a solid state disk a few classes ago. I forgot to bring it again, but it doesn't look any different from a traditional disk. Works very differently. Okay, solid state disks are like RAM. Okay, they don't have any moving parts. Okay, they are also simple examples of solid state disks are these SD cards that you have that you put in cameras or even in cell phones. They're all solid. They're all solid state memory. Okay? So it's simply think of it as a non-volatile storage where your disk is partitioned into blocks. Okay, they're linear 0 through n, and you can simply send in a request for any block I. You can access block I at random and read the bytes that are stored there. Okay, just as in RAM, you can go and say read address I, okay? And you can just go and read whatever is stored at address I. If you read address J, there's no such thing as I have to now reposition my memory to go and read, reposition something in memory to go to read address J. You can simply go and randomly read whatever location you want. Okay, SSDs are basically going to give you that abstraction. Okay, it's flash storage. Okay. Any compact flash card, SSDs, not SSDs, SD cards, micro SD cards are all examples of flash storage. Okay, now you get entire disks that use the same technology. Okay, they are a lot faster because you don't have this notion of a seek, you don't have the notion of rotational latency. You can simply go and simply read that block. Okay? There's no time other than for the disk driver to send the request to your disk controller. There's no other latency involved in reading or writing data. Okay? So very fast reads. Writes are a bit slower on solid state disks, okay? And that's nothing to do with the electronics itself. The reason writes are slower is on magnetic disks, you can simply overwrite data by writing new data to that location. In solid state disks, you have to first scrub that block. Okay? That's called an erase cycle. Okay? You can't simply overwrite data. The technology doesn't allow you to do that. You have to first zero it out, reset it, before you can then go and write new data. So rewriting a block, okay, typically requires a reset of that block. You can't simply go and write new bits at that location. You can do that in a magnetic disk, okay, but not in a solid state disk. So writes are slower because they need a reset or an erase before you can do an overwrite. Okay. So typically what file systems do is if you want to change what is on block I, you don't pay the cost of overwriting. You simply write that block at some new location and you just change the inode to point to that new location. If you remember the way file is organized, we said you have an index node. An index node is a bunch of pointers to where the block is stored on disk. And let's say that's your disk. So you have one pointer here, another pointer there, pointer here, and so on. So if you now write to this block, okay, typically in a magnetic disk, you'll go and overwrite this location. Okay, in a solid state disk, you'll write that block, the new block at some new location, and simply update this pointer. And the reason for that is if you write to an already reset location, that's going to be faster. If you try to overwrite to this block, you have to first reset it. Okay, you have to do an erase, scrub that location, then write. Okay, that's going to be twice as slow, at least. Well, typically, it's much slower than that. Okay. So what you do is you don't overwrite, you write to new location, and then you garbage collect later. This block that now was overwritten to is now not in use in the file system anymore. It's just sitting there. Okay, periodically, you will go and start doing garbage collect. All of these blocks that are inactive have been overwritten. Okay, you will reclaim by running a background process that goes and starts doing an erase on each of those blocks. Then they're ready for use again. Okay, this is how the technology works. Okay, so there isn't. You don't do this in RAM. In RAM, you can simply go and rewrite to a page. Okay, in solid state, this you don't do that. Okay, because there you have to do a erase. Yes.
How do you save the list of blocks you have to garbage collect? Because if you do it in memory, then you just lose blocks if the thing crashes.
Yes. So there is all sorts of additional optimizations that are going on to track which blocks are free and ready for writing, which blocks are not in use but needs to be recycled, and not recycled, rather garbage collected. You need to do an eraser. So you have to have all this additional data structure. So in normal file systems or disk, you only have a free block list. Free block list are all the blocks that are not in use. You can use them to store some data. Here you will have to have a free block list, you will have to have a list of blocks that needed to be garbage collected and so on. Additional structures have to be maintained by the disk and the disk controller. Okay. The other thing that you have to do, which is very important in solid state disks, is there is a limit on the number of writes you can do to a block. In a magnetic disk, typically you can overwrite the block as many times as you want until your disk as a whole dies. There is no such problem. Okay? In solid state disk, there's a limit on how many times your block can be erased. After a while, the block basically wears out, so you can't use it anymore. Okay? So typically, early technology says you can do it 1,000 times. Okay, now it become 10,000, 100,000 erase cycles are possible. Okay, but still, if you try to refuse, the same block is written to over and over again. After a while, the block is going to wear out, and then you basically cannot use that block anymore. That part of the disk becomes unavailable for use. So other optimizations that are done by the disk is what is called wear leveling, okay, which says wear out the disk at the same rate. Don't wear out some blocks more than others. So if there is some block that has been recycled or erased 1,000 times and another block only 10 times, this block is older, it's going to wear out faster. Okay, so if you have lots of free blocks, don't treat them as any free block will do. Pick, let's say, a block that hasn't been erased many times and increase its age, because that other blocks have aged faster. Okay, they are going to wear out sooner. Okay, so you want to do such optimization. This is like how the tires of your car wear out. Okay, typically you want to rotate them so they wear out at the same rate. Okay, the same kind of optimizations are done here. Okay. All new considerations that come into play. Okay, none of the old ones are here anymore. You don't have to worry about seek, rotational latency, but you do have to worry about things like how many times have you written to this block. If you keep rewriting to that same block faster than you rewrite to other blocks, that block will die sooner, and then the block becomes unavailable, even before the disk as a whole dies. Yeah, so you have to do wear leveling, you have to do garbage collection. All of these other issues come into play. Yes.
So like once one block dies, is the entire drive done, or is it just you have less storage now?
If the block dies, you have less storage. The rest of the disk is perfect. Each block has a lifetime. That says how many times can it be used to store active data. Okay, if you reach the lifetime of a block, that block cannot be used, but other blocks are still available. So the storage space that you have on your disk will reduce.
Does it ever so like you keep writing to that, like can it wear out before that and then just now you have corrupted data, or does that ever happen?
So question is, can it wear out before that? So typically the way the electronics is built is you have a safety threshold that is much lower than the actual time it takes to wear out. If it can sustain, let's say 20,000 cycles, you will conservatively set to 10,000. But it's not like it's waiting for 20,000 to be hit. It may be 100 cycles before that or 100 cycles later. That's the approximate lifetime. So you set the threshold to be much lower and just mark it dead even before it's actually dead. But you don't want data corruption. Right? So that's how they will actually implement your disks. Okay, so now the only thing to keep in mind, sort of other than all of these other factors, is solid state disks are significantly faster. Okay, because there is no seek or no rotational latency, significantly faster, so they allow you to have much higher throughput. Okay, so they are used on servers, they are used for high-end I/O applications, databases that do lots of I/Os and things like that. On personal computers like laptops, they are not necessarily used to give you faster access, although that's a nice feature to have. They are used primarily because they consume less energy. Okay? There are no moving parts. There's no motor that's spinning the disk. Okay, your battery will not die if the motor doesn't keep out of spinning. Okay, so the lifetime of your laptop or tablet will increase significantly if there is no motor that needs to keep spinning. Okay, because if you don't need to do any I/O, the disk is just sitting there waiting for the next request. It's not consuming any energy. Okay, so on low-end devices, I shouldn't say low-end, in personal computing devices, mobile devices, this technology is used to increase battery life. In server devices, it's increased for its speed. Even in laptop, speed is nice, but that was not the reason they started putting this device, because they are still expensive. It is there only to increase your battery life. Yes, question.
What what would you say has a longer lifetime, a solid state or a
So what has a longer lifetime? I think that now the technology has improved to a point where with typical usage pattern, a disk will last several years. Okay, so people throw away electronics before the life is actually reached, right? So you buy phones for whatever reason every 2 years, doesn't mean your phone died in 2 years. You just want the next good best thing that has come along. So the technology has improved to a point where people buy newer devices faster than the disk dies. Okay? Very early versions of the disk, you have to be very careful because if you did not do air leveling or something like this, the disk would die with high I/O throughput application in a year. Okay? That's no longer the case because they have improved it to a point where several years is normal. Even for magnetic disk, several years is normal because eventually the motor will give in. Okay, or something will happen and the disk will just die because the electronics on it also has limited lifetime. Okay, so a few years is what you get out of these, both of these types of technology. Okay, so that's solid state disks. So we have two more things to talk about: tertiary storage and disk arrays, and then we'll be done. We'll move on to the next topic. Okay, tertiary storage I'm going to do very quick. Okay, so disks are referred to as secondary storage. Okay, RAM is primary storage on your machine. Disks are secondary storage. There is another tier of storage called tertiary storage, which is typically slower and larger capacity than disks. And the main example of these are tape drives. They are usually tertiary storage is used for long-term archival and backup. It's not used for live data access. You want to put your data on some long-term storage because maybe 3 years from now you may need it for whatever reason, backups or whatever. That's the type of storage you use. Okay, for a long time, tape drives were a classic example of tertiary storage. If you think about how tape drives work, okay, they work the same way how VHS tapes on VCRs work. If you know what those are, people don't use them either anymore. So they are linear access devices. They are not random access. Okay, so if you think about it, if you use the VCR tape and you wanted to jump to the 50th minute of your movie, you have to fast forward there and wait for the tape to actually go to that location. Same is true in tape drives. Okay, tape drives are exactly the same. So if you want to go and read what is at the end, you have to keep spinning the tape until you reach to that location, then you can read and write. Okay? So they're meant mostly for linear access. They're not good for random access at all. Okay? For backup purposes, that's good because you're simply dumping data on a tape and it's just recording linearly. Okay? And retrievals, if your disk dies, maybe you can wait for a slow linear access device to get you the files that you have stored on that tape. Okay, but it's not for random access. You can't run a real application using tape storage. It will be far too slow. Okay, so tertiary storage devices are mostly used for backup purposes. Tapes are a good example. Okay, you use DVD-ROM, CD-ROM, optical drives are another examples. There is this whole class of devices called robotic jukeboxes, very similar to what you have in restaurants where basically you say, go play this CD, it pulls that CD out and pops it in. Same is true here. Okay, your tape drives, there's an array of tapes. You say, go get the 10th block on the 5th tape. Okay, so this thing is going to pull the 10th or whatever, 5th tape out, it will load it, it will spin it up, it will read the block and then it will eject it and put it in. So instead of a human doing all of this, there's a tiny robot that will just pull the right tapes from the right array and stick it in. And they're very expensive. So what has happened is disk drives have fallen in price so much that they've essentially taken over whatever tapes used to do. So you can buy a terabyte disk for $100. Okay, so the technology has improved to a point where it's better to use cheap disk drives for backup, okay, for backing up data that's stored on another disk rather than buying a tape drive. Okay, you can buy removable external disks, you can buy other kinds of disks. So tertiary storage is effectively going away the way we have seen it in sort of the past decades or so. Your tertiary device and the secondary device are one and the same. They're hard disks. Okay, just that for tertiary storage, you can make do with slightly cheaper disks of higher capacity because it's used for things like backup, not live data access. Okay, so, but that's the thing to keep in mind. Saying falling cost of hardware has meant that disks are cheaper now than tapes. So you just use disks to do back up other disks. Okay, but there is that layer still in the hierarchy where you store data for long-term purposes. Okay, so tapes I already talked about. So the last point in the last 5 minutes I'll talk about is what is referred to as RAID storage. Okay, so in large servers, okay, you don't have a single disk to store all of your data. You have multiple disks. Okay, you have more than one disk. And what happens when you have multiple disks is rather than treating each disk as an individual storage device, you take a collection of disks and you construct a larger logical disk that makes it look like all of these disks are like one bigger disk. Okay, so there's a picture to keep in mind. Okay, let's say you have 3 disks. If these 3 disks were accessed as independent disks, okay, you would actually see 3 volumes on your server. Each is a separate device. Each will have its own directories and so on. Okay. This, in the industry parlance, is called JBOD, just a bunch of disks. A very silly acronym, but that's what it is called. Okay. Now, most servers won't actually use disks in this way. Okay. They will in some cases, but if you are a large storage server, what you will do is you'll take all of these disks and you'll construct one large logical disk out of it. So from the file system's perspective, okay, these 3 disks appear as if they are one bigger disk, which are the total storage capacity of all of these disks. And internally, your disk array controller is going to decide when a block comes in which of the disks to store it on. These kinds of storage devices are referred to as disk arrays. It's an array of disks that is to the OS appears as if it's one large logical disk. Okay, there is a hardware controller that is going to make it look like these 3 disks act as one single bigger disk. So one form of a disk array is referred to as a RAID array, redundant array of independent disks. Okay, there are many levels of RAID. There is no reason to go into all of those levels. There's just the most important point to keep in mind is when your disk arrays, 2 important things have to be taken into account. One is when a file is stored, all the blocks of the file will not necessarily be on the same disk. Okay? The blocks of the file, let's say this is a file, is chopped up into disk block. You may have the first block going on disk 1, second block going on disk 2, third block going on disk 3, and so on. Okay? A file may be scattered across multiple disks, something we have not seen so far. Okay, we said file may be scattered across different tracks, but here we generalize. Every file may be chopped up into blocks, and the blocks may actually be stored on different disks, different physical disks. Okay, from a logical disk perspective, it looks like the blocks are all stored on the same logical disk, but internally they may be scattered across physical disks. So to access a file, you may have to go to multiple disks and retrieve different parts of the file from those disks. Okay. Yes?
If you remove any of those disks, how would that affect the system? If you
Yeah, so if the problem with this approach is if you lose a disk, okay, if you have this JBOD construction, if you lose a disk, only files that are on that disk will go, they will fail. In this abstraction, if you lose a disk, meaning a disk fails, there's a hardware failure, all files become unavailable because each disk stores parts of every file that's on your file system. Okay, so to address this issue, this is why we have what is called RAID. We have a redundant array of inexpensive or independent disks. So you have to store additional information to deal with disk failures. What you don't want is one disk going down. Let's say you had constructed an array of 100 disks. One disk went down, all the data on your system is gone away because that disk stored blocks of every file that was stored on your system. So the way this is handled, the simplest way to understand this is you basically keep extra data to allow you to do recovery. Okay, the simplest form of redundancy is called mirroring, and that's the only one we'll talk about here. Okay. So what happens in mirroring is you store 2 copies of every data block on 2 independent disks. Every block that you store in your file system, there's one copy of it is stored on one disk, another copy of it is stored on another disk. So there's a mirror for every disk. For whatever data is stored on one disk, there will be an exact copy on another disk. So if this disk goes down, there's a second copy available. Simplest form of redundancy. Okay? It's expensive. It's going to double your hardware cost. You need twice as many disks to store some amount of information. But you can deal with disk failures. A disk can entirely fail. In fact, one half of the disks can fail, still your system will be functional. There will be no data loss whatsoever. Everything will be transparent. Okay, the hardware will show a red light, will start flashing saying this disk failed, system will continue to work. You can just pull out that disk, put in a new disk, and everything will be back to normal. Yes, question.
When the disk failure occurs, do we mirror the duplicate again?
Yes, so when a disk failure occurs, let's say this disk went away, all the requests are transparently forwarded to the mirror by the hardware controller. Okay, at some point in time, you will pull this disk out and stick a new disk in, which will be a blank disk. The I/O controller will go do what is called reconstruct. It will take all the data on the mirrored disk and put it back there. So now you have two copies again, and you will go back to normal. Okay, so all of this is done transparently. The OS doesn't do anything. The hardware controller will do it for you. Okay? This is how large servers work. Okay? They have disk arrays because there's a lot of data. Okay? So all the data that you store in a server doesn't fit on a single disk. So you construct arrays of disks. But when you have arrays of disks, you want to deal with failures in some reasonable way. The way you deal with failures is you have redundancy. And mirroring is an example of redundancy. There are more sophisticated schemes like parity, which you don't have to worry about here. It's just another way of storing redundant information such that if one disk fails, there's enough redundant data to reconstruct whatever is on that disk. So no data is lost. Okay. That's the way to think about parities. You will see that there are different levels of RAID. RAID 1 is what I refer to as mirroring. It's the simplest form of redundancy. You can go all the way to RAID 5 and RAID 6 and so on. Different schemes for redundancy. Okay. The basic idea is still the same. You don't want data loss if the disk goes down. Okay, but we'll not talk about other levels here. Okay, just focus on RAID. Okay, so we ran out of time, so we'll just stop here today and continue this discussion on I/O next time.